Hello, this is Dr. Barang Askarian. I am an associate professor at Washington State University in mechanical engineering. My area of expertise is fluid mechanics. I'm also a licensed professional engineer at PE in Washington State in thermal fluids. This is the beginning of the heat transfer course, the university level heat transfer course. And so in this session, we're going to talk about like the phenomenon of heat transfer. We're going to introduce it. We're going to kind of relate it to thermodynamics. We're going to introduce the first law of thermodynamics and some of the applications of it. And we're going to move on to different mechanisms of heat transfer. It's just an introduction to heat transfer as the first session. The first thing that I want to talk about is the book. And I'm sure as a student of mechanical engineering, you already picked your book. That's why you are here, and you have some book in heat transfer. So the book I'm going to use is the book Heat and Mass Transfer by Yunus Çengel, this book. And, if you are, again, a student of mechanical engineering, you are familiar with this particular author because he has books in thermodynamics and fluid mechanics also. They're very good books. I've been teaching these books, all three of them, pretty much for, I guess 7-10 years. And compared to other books, they are way more understandable to me. And it depends. But students also seem to like them. So that's the book I'm going to follow. And let's just get started. So heat transfer, I'm going to give you an example that everybody has seen, everybody has experienced that. We have a cool can of soda, right? And you put it on the table in the room is warm, and that can of soda is going to warm up after a while, right? The opposite is when you have the warm can of soda that you just bought from the grocery store and you put it in the fridge, and it's going to cool down after a while. Both of these are different cases of heat transfer, right? And so what you have learned in thermodynamics as the zeroth law of thermodynamics, and sometimes we talk about it in the second law of thermodynamics, that heat will be transferred always in the direction of decreasing temperature. So heat, in order to have heat transfer, in fact, you need to have a high temperature and a low temperature. And heat goes from the high temperature to the low temperature, right? So in order to have it. And but the thing about the heat transfer and thermodynamics is this. Thermodynamics, using the first law of thermodynamics, sometimes the second law of thermodynamics, you can calculate the amount of heat transfer in terms of joules, right? Sometimes kilojoules. But most probably, you can't calculate how long it took. You have one state, like the beginning state, and the last state. Let me give you an example. This is a thermos, right? And you put like boiling water in it or a hot coffee in it. You kind of expect it to last, for the hot coffee to stay in there hot for, I don't know, 10 hours, 24 hours, whatever, depending on the brand that you're getting. And so you can calculate it using just a basic Q equals MC delta T, that when the temperature, if you know the mass of coffee here inside the thermos, and if the temperature drops from 90 degrees Celsius to like 80 degrees Celsius, you have the delta T, and you can calculate the amount of heat transfer in joules, can't you? But thermodynamics gives you that. That's not the problem. But what you're interested in, if you are the designer of this thermos, is how fast heat is being transferred. Because we know that the amount of heat transfer from 80 degrees from 90 degrees to 80 degrees for this amount of mass of coffee, we can calculate it in terms of joules. But we want this to happen over like, I don't know, 24 hours. We want it to happen very slowly if you are the designer of this thermos. That's where heat transfer comes in. The whole science not only can calculate the amount of heat transfer, it can also calculate how long it takes. Heat transfer mostly is interested with the rate of heat transfer, this course. in terms of watts or kilowatts. Yes, of course, in thermodynamics, when you're dealing with steady state processes, also the first law of thermodynamics, you're dealing with watts, like work could be watts and heat transfer could be watts. That's true. That's one way to calculate heat transfer. Heat transfer gives you a variety of options when it comes to different cases to calculate heat transfer. So I wanted to tell you that first. Then, as we talked, we said before, in order to have heat transfer, we need to have some temperature difference, temperature, hot temperature and cold temperature. If you have two bodies that have the exact same temperature, there's not going to be any heat transfer between them. We know that. So that's like a fundamental law of our universe, the universe that we are living in. We kind of see like similar, phenomena other places. Like when it comes to pipes, you learn it in fluid mechanics most probably, that in order to have flow rate in the pipe, you need to have pressure difference. In this case, pressure difference is very much like the temperature difference that I just talked about. Or when it comes to gravity, in order to, well, when it comes to like dropping something, looks like everything goes from higher elevation when there is no resistance in front of it to lower elevation. It loses elevation, just like the hot body loses temperature, basically loses heat to cool down. That's how it works. And even in like circuits, again, you have two different points that have different voltages, and the voltage happens to go from the high, the current happens to go from the high voltage to the cold to the low voltage. So again, same thing. In order to have heat transfer, I need to have temperature difference. In order to have flow rate in a pipe, I need to have pressure difference. In order to have current in a circuit, I need to have potential, voltage difference. They are, in a way, the same, and we can actually use that circuit model in heat transfer. We're going to talk about it later, which is a thermal resistance network. So this is an introduction to heat transfer, and why we have a different course on heat transfer, because we already had like thermodynamics, and thermodynamics talks about it in the first law of thermodynamics. And what we're interested in is different ways to calculate heat transfer that thermodynamics can't. There are thermodynamic situations that thermodynamics cannot calculate heat transfer. You need another equation to calculate it, and heat transfer will give you that equation, and also how fast it happens. All right, so let's say, all right, this is a decent introduction to heat transfer. Next question is this: what are the applications of heat transfer? Heat transfer is pretty much everywhere. From your body keeps losing heat. And in fact, let me give you this example. Have you ever felt cold or really warm? The feeling of cold or warm is because of this. Your body is generating heat all the time. When you're sleeping, when you're running, when you're hiking up a mountain, when you're walking, when you're sitting in a chair, your body is generating heat. The difference, the thing is that your body is generating different amounts of heat transfer in terms of watts for different activities. When you're running or when you're hiking up a mountain, you might even be able to hike up a mountain or climb a mountain in a t-shirt in winter. Why? Because your body is generating so much heat. But on the same day in winter, if you're walking down the street, you probably need a puffy jacket or something. Because, well, what's the difference? It was the same winter day. I was hiking up the mountain with nothing, with just a base layer. And now I have to have a puffy jacket. And when you're asleep, then again, your body is generating some heat, but you need like a comforter. You need something like that to be able to sleep well. So what's going on here? The thing is that your body is generating heat all the time, but it's generating different amounts of heat in terms of watts, right? And whenever your body is losing more heat than it's supposed to, you feel cold. When your body is losing less heat than it's supposed to, you feel really warm or hot. And when it's just the right amount, you feel good. You're like, this is good, I'm good to go. That's the case when you're running in winter with a base layer. So the amount of heat that you're losing actually is decent. You're losing a lot of heat, but it's cold outside. And because your body's generating a lot of heat also at the same time, it's somehow okay in that situation. But if you stop after you're running and you don't wear a puffy jacket, you're going to feel cold. So that's one application, right? The other application is like a CPU fan in your computer, a radiator in a car, a fridge. A fridge is a refrigeration cycle. It has an evaporator. An evaporator is a heat exchanger. It has a condenser. A condenser is a heat exchanger. In a power plant components, in a power plant, what do we have? We have like a pump, like a Rankine cycle. We have a pump. We have a boiler. A boiler is a heat exchanger. Then you have the turbine. There is some heat transfer in the turbine also, if it's not adiabatic. And also the condenser. So it is pretty much everywhere. It is where you want to calculate the like the optimal insulation thickness for the wall or for the roof. So it shows up everywhere. Heat transfer pretty much is like after you take thermodynamics and fluid mechanics, you apply both of them in this course to calculate heat transfer, and you see the applications everywhere, like solar collectors. Why is it that, you know, when you park your car in the shadows, even if it's a hot day, it's okay, but if you park your car like in front of the sun, it might even ruin the dashpad. That has happened to me, like, right? So these are different examples of heat transfer. Now, so we introduced the book. We just gave you some introduction to heat transfer. We're going to talk about the different mechanisms of heat transfer. But before that, I'm going to go over something that you should have learned in thermodynamics and fluid mechanics before, and most probably you have. But let's just do a quick review of the first law of thermodynamics, because we're going to apply the first law of thermodynamics in heat transfer a lot. You might apply the like the steady state form of the first law of thermodynamics, or you might apply the unsteady form of it. So we have to introduce both cases, because we're going to use both cases in the derivation of equations, and it's going to help us a lot. And that's a beautiful law. I mean, I love the first law of thermodynamics anyways, right? All right, let's do this. So now we are going to talk about the first law of thermodynamics. Before talking about that, we have to go over like some definitions that I'm sure you're familiar with, but very quickly we go over that. The first thing is basically a system, right? So that's what you learned in thermodynamics and in fluid mechanics. We said we have two types of systems. What was a system? I'm going to go over it very quickly. A system was if you just put some boundaries like this around the fluid, or sometimes it's not fluid, it's just solid, and a space that you are a space, an area in the space that can contain mass, right? And it is defined by the boundaries, these boundaries. You decide what boundaries you want to, choose for the system. So you have the boundaries. That's just system. Done. Now, if you remember, we had two types of systems in thermodynamics and fluid mechanics. The first one was a closed system. And a closed system basically is a system like a piston cylinder system, something like this, right? And this would be the mass inside the system. A closed system simply is this, that there is no mass going into the system or coming out of the system. Basically, there is no m dot going in. M dot going in is 0, and m dot going out is also 0. No mass goes in, no mass comes out of the system. Done. That's a closed system. And as opposed to this one, we have an open system. So an open system is a system that basically, so if this is like A, a closed system, and then B, an open system like this. An open system is a system that, m dot in and m dot out are, m dot in could be non-zero, and m dot out also could be non-zero, something like this. So that's the difference between an open system and a closed system. So I'm going to move this here, so my picture is not blocking the definition of it. I guess now it looks way better. So let me move this one here too, make it look better. There you go. So now everything should be good to go. All right, so now we have the open system and the closed system, right? Basically, if you remember in thermodynamics, we just called the closed system just a system. We just called it a system. And an open system, we called it a control volume. And a control volume also, sometimes we show it by CV, like this, right? Okay, so we got the closed system, open system, and system control volume. Done. In heat transfer, we use it. In thermodynamics, we use it everywhere. In fluid mechanics, used it. You remember, like a section of a pipe was just an open system. A turbine in thermodynamics was an open system. A piston cylinder was a closed system, and we studied the mass and the changes that it goes through, throughout the process. All right, that's the first thing that we want to know. The second thing, after defining the system, is a property. And a property, you know what a property is, certain characteristics of the mass inside the system, and or the mass that goes across the boundaries of the system. Go back to thermodynamics and review what the property was, but just to give you an idea, and you already know it, temperature is a property, right? Pressure is a property. Internal energy is a property. Entropy is a property. Enthalpy is a property. All of it, even velocity that I'm showing by like capital V here, is a property of the mass that comes in, goes out, or the mass inside the system. You can have a moving control volume that has mass that is moving. That mass has velocity, so that's a property of the system. Okay, so property is some certain characteristics of the mass of the system. Viscosity, another one, right? All of this. Thermal conductivity, that we're going to talk about a lot in this course. All right, cool. Now, after this, we define a property. There's something else that we define, and that's a state. State is when you look at the system, inside the system, any combination of properties can give you one state. I'll give you an example. Imagine that we have a tank. We have a tank full of air. In this case, this is a closed system. Let's say all the valves are closed, everything is good to go. Let's say the temperature inside this tank is 20 degrees Celsius and the pressure is 1 atmosphere. And let's say I'm going to just heat up this tank, right, with a flame or whatever. I'm going to heat it up, but still a closed system. And what happens at the end, it's still air, right? But the temperature becomes like 25 degrees Celsius, and let's say the pressure goes up to 110 kPa. So 1 atmosphere was already like 101 point like 325 kPa, right? That was the beginning. So at the beginning, it was 101.325 kPa, but at the end, it is basically like 110 kPa. Does that make sense? So we went from one state to another state because we had one combination of properties at the beginning That was state one. And at the end, I have a different combination of properties, which I call it state two. Now, based on this, I'm going to define something new, which is also called a process. A process is when you go from state one to state two. That's what a process is. So we define the system, we define the properties, right? We define the state, any combination of properties. Now, if you go from one state to another state, the path that you took, this path, is called the process. Now, if you remember from, again, thermodynamics, we had some processes like isothermal processes, right? Which is the temperature doesn't change in that process. Or isobaric processes, pressure stays constant. Or constant volume process, where the volume is constant, but other things change. In fact, in the last example that I just gave you here, if I scroll up, this example, this particular example, this was a constant volume process. So we didn't change the volume of the tank, we just heated it up, right? And then at the end of the process, we had air, same amount of air, because it was a closed system, with different pressure and different temperature. So that's a constant volume process. So now looks like we kind of reviewed these things. Now that we have these, we can actually comfortably move on to the first law of thermodynamics. What do I need a state and process? Because, you know, sometimes we deal with steady state processes. And that's also a process. And then it shows up in the first law of thermodynamics. So we want to address it there. All right, let's do that. Okay, first law of thermodynamics. Well, if you have studied fluid mechanics, there is a theory in fluid mechanics that is called the Reynolds transport theorem. Sometimes we show it by RTT, Reynolds transport theorem. Reynolds transport theorem says this, that if I have a control volume and I'm looking at some intensive property, some extensive property, I'm sorry, then there is this law that they actually prove it, that that property is going to follow. I give you first an example. Let's just talk about intensive and extensive properties, because I talked about properties and I forgot to talk about intensive, extensive properties. That's fine. So we said properties in fluid mechanics and heat transfer and thermodynamics. There are two types of properties. There is the intensive property and there is an extensive property. An extensive property that is dependent on mass, basically. A good example of an extensive property is mass itself. The more mass that you have in the system, the more mass you have in the system. That's it. So volume, that we show with the V with the line through it, because we have V for velocity in fluid mechanics, and we show V with the line through it to kind of, you know, differentiate. And capital form of energy in terms of joules, not joules per kilogram. Capital form of enthalpy in terms of joules. These are extensive properties, right, of the system. Volume, volume, I showed the volume already. So these are extensive properties. Intensive properties are the properties that if you get the extensive properties and you divide them by unit mass, then you get the intensive property. Like if you divide volume by the mass of the system, what do you get? You get the lowercase v, which we call it the specific volume. If you divide that capital E in terms of joules and you divide it by mass, you get the lowercase e in terms of joules per kilogram. If you want to write it down in your notes, go ahead, do it. and we call it the, the energy of the system. And if we get that capital H enthalpy in terms of joules, and you divide it by mass, you get the lowercase h, and we call it the enthalpy, the specific enthalpy of the system. That's, that's what we do. Again, let me move these to here so my face doesn't block them. I'll do that. Like this. So I guess this is better. Intensive and extensive properties. Now, Reynolds transport theorem says, let's say we have, so I'm going to move to Reynolds transport theorem and I can get the first law of thermodynamics out of it. RTT, Reynolds transport theorem. It says we have a control volume, right? That's the control. Okay. There is an extensive property. This extensive property could be energy, could be momentum, could be, I don't know, something, right? Mass. Mass is an extensive property. I'm going to show that extensive property by a capital B. So this B could cross, because it's an open system, could cross the boundaries of the system, go in, can also come out. And we might actually accumulate or lose some of this in the system. I can give you one example. Imagine that you have, let's say you have a pipe like this, right? This is a pipe, it's an open system. Water is going in, and because I want to show energy. Water is going in, has some kinetic energy, has some temperature, which is internal energy, all of this, right? And comes out. And let's say I put a flame here like this, and I heat up the water that already has some energy in the pipe. Now, not only that, I also don't keep the flame a constant flame. I just increase that flame. So like right now, water is going in and then gets heated up and comes out. Okay, sure. Goes in, gets heated up, comes out at minute 1. Now at minute 2, I'm going to increase the flame. So what's going to happen? What's going to happen is the energy content in the control volume, this one is not going to stay constant either. This is going to increase also. So not only you have the E dot in and E dot out, there is also going to be, if you just look at the control volume, the energy content of it, because I'm increasing the flame, if you just look at the water in the pipe compared to 2 minutes ago, that water in the pipe is hotter because I increased the flame. Does that make sense? So this is the case that you have an extensive property in the control volume. Some of that extensive property is carried with mass and comes in, and some of it, goes out with mass. But inside the control volume, it can also change if the process is not steady state, which we're going to talk about. All right, so what Reynolds transport theorem said is basically this. This is what you learned in fluid mechanics. That when you have this B in and B dot out, Reynolds transport theorem says, okay, RTT basically says B dot in minus B dot out equals the change of B in the control volume, like this. And of course, you can add one more term here to make it more comprehensive, as that's B dot gen, because like B could be capital S, entropy. Basically, that would be second law of thermodynamics comes out of this. If B is capital S, that's the second law of thermodynamics. So this, I give you one example, right? A cool example would be something like this, that we'll look at like a classroom. M dot out plus M dot gen equals dm of control volume dt. Imagine that, let's do this, change the color. That's cool. Imagine when we were talking about a classroom. A classroom, M, let's say mass, represents the number of students. M dot N is the number of students per minute, per second. Students who actually walk into the classroom, right? And M dot out is the number of students per minute or per second, per unit of time, basically, that are walking out of the classroom, walking out of the door, right? And M dot gen is, well, no students gets generated in this case in the classroom, hopefully. So that would be 0. And then this dm CV over dt is the rate of the number of students in the classroom. How does that work? Let's say I have like 2 students per minute, 2 students per minute that are walking in. So every minute, 2 students walk into this classroom from the door. Also, every minute, 1 student walks out of the door. No students gets generated in the classroom. What happens is, during that 1 minute, if you just look at the control volume, the number of students in this class goes up every minute by 1 student. Does that make sense? So every minute, 2 students walk in from the door. 1 student walks out. So if you just look at the control volume, which is the classroom, the boundaries of this classroom, every minute, the number of students in that classroom is 1 student more than the previous minute. That's the change of property, in this case, mass, of this control volume. So, and this could be applied to like energy, to entropy, to everything. If you apply the Reynolds transport theorem to energy, you get the first law of thermodynamics. If you apply Reynolds transport theorem to entropy, capital entropy, you get the second law of thermodynamics out of it. And that's what we're going to do. We're not going to do the second law. We're going to just do the first law, and then that would be our session. And then after that, next session, we're going to talk about heat transfer, which is one of the terms in the first law of thermodynamics. But whenever we want to, analyze any system, we have to write the first law of thermodynamics first and just cancel a bunch of terms that we don't need, and then we can look at the heat transfer and somehow find a way to find it, right? All right, let's do that. Okay, let's say B, that extensive property that I just talked about, change the color of this. Heck. B is energy. Okay. And what is energy? When it comes to energy, well, energy is associated with mass, basically. Energy is a combination of 3 things. It's a combination of internal energy plus kinetic energy plus potential energy. So if you're taking notes, write that down in your notes. This is the internal energy, right? Internal energy. That's the kinetic energy. And that's the potential energy. It's a combination of these 3. That's energy, right? Okay. Now let's apply Reynolds transport theorem. If I apply Reynolds transport theorem, it's going to look like this. It says for a control volume, E dot in minus E dot out plus E dot gen. If you are generating energy in the system, let's say there is like a chemical reaction or something like that, equals the change of energy in the control volume, like this. Okay, now let's apply it. Let's see what types of, for a control volume, what types of energy are we dealing with that are going in and out of the system, right? So the right-hand side term is okay. It's like the change of kinetic energy, right? So the one that I have here, kinetic energy, potential energy, and internal energy, these three, that's the right-hand side of the equation. That's the energy of the control volume. It's not a problem. You can take the derivative of all these three and, you have the right-hand side. Let's take a look at the left-hand side. So if this is my control volume, what types of energy that I have that are going in and out of the system? So I'm going to show a big control volume like this. This is my control volume. Okay, I'm going to use a different color. Maybe red would work. Let's see. Let's do red. Yeah, red would be good. Now, when it comes to energy that is going in and outside of the control volume, what types of energy do we have? Okay, energy could be in the form of heat transfer. You learned that in thermodynamics. Then it can go out of the system in terms of heat transfer also, right? Energy can go into the system in terms of work, W dot in. And it can leave the system in terms of work. Now, there is something that we need to address here. And I want you to write this down in your notes. This is a common problem among students when it comes to heat transfer and work. Write it down. Are you ready? In heat transfer and fluid mechanics and thermodynamics, the energy that is transferred to the system through the boundaries without mass is called either heat transfer or power or work. Power or work are the same. Heat transfer and heat transfer rate are pretty much the same. Like heat transfer is Q, heat transfer rate is Q dot. Work is W, or power is W dot, right? But in these cases, mass is not going out of the system. You can have a piston cylinder system, which is a closed system, and you can have both work by, the piston can expand and, then it can actually move an object and do some work, and you can heat it up also. That's heat transfer. None of these cases used mass of the fluid to enter and, to enter the system or, to force it out of the system. Does that make sense? This is something that's very important and is a common mistake. So one more time, energy that is transferred to the system or comes out of the system without mass, just through the boundaries, is either heat transfer or work, or heat transfer rate or power. Q and W, Q dot and W dot. Be mindful of that. You need that in all these three courses, right? And thermal system design also. Now, energy can also be transferred with mass. The mass that comes into the system has energy with it. It can carry energy into the system and it can carry energy out of the system. Okay, so let's show that. So I'm going to modify the boundaries of my system because of this new, so like this. So I'm going to modify these two. Oh God, what did I do? I can fix it. Then I have to, all right. Let's do it this way. There you go. Now, there you go. Now it's good. Now what do I have? Now I have mass that goes in. Mass that goes in carries energy with it. And mass that goes out carries energy with it too, out of the system. In terms of velocity, in terms of internal energy, in terms of potential energy, and in terms of something new called the flow work. because we have an open system. So let's just talk about the energy that goes in and the energy that goes out. So that gives you some sort of energy in and energy out. So I'm just going to say that m dot times the energy that goes in, energy that, let's just show it this way, some sort of energy, energy in, and of course we have m dot n times, so let me show it this way, m dot n times energy in. So this would be energy out. I'm sorry, let's fix that. Now it's good. Okay, so now let's discuss these ones one by one. And of course, the right-hand side of this equation easily is going to show the change of energy in the control volume. So we don't have to worry about that one. That is the change of energy in the control volume. All right, cool. So let's talk about different forms of energy. I want you to write down this diagram, show it in your notes and everything, do this whole process with me, because that's the only way to actually learn. And there's a big reason that I'm not teaching by PowerPoint. Writing something with hand gets it in your nervous system. The act of writing, when you have notes, when you're taking notes, it gets it in your nervous system. You think about it more. And that's why PowerPoint puts people to sleep. We're going to use PowerPoint when we want to show some pictures and stuff. But mostly, we actually write down things. That's how you learn, in fact. So take notes for sure. Intentionally, I'm doing this. All right. So let's derive the first law of thermodynamics. All right, let's see what we have. We said Reynolds transport theorem says that this is what we were looking for. B dot in minus B dot out plus B dot gen equals dB of control volume dt. We just said, okay, B is supposed to be energy. So I have E dot in minus E dot out plus E dot in gen dot in gen equals dE control volume dt. Cool. So what is E dot n? E dot n is, we said, could be Q dot n, could be work, power in. This equation is in terms of watts, by the way, because it's E dot. It's not joule. All right, what else do we have? Oh, I can have m dot in times the internal energy in, right, times the kinetic energy in, which is the Vn squared over 2, times the Gzn, plus one more term that we call it the flow work. Flow work, I'm not going to talk about it here. Why do we have flow work in open systems? You've got to go back to thermodynamics or fluid mechanics. Eventually, I'm going to post some courses in thermodynamics and fluid mechanics that are going to cover that, right? So, but when you have an open system and the mass is crossing the boundaries, on top of these three, internal energy, kinetic energy, potential energy, one more term shows up. And you can prove it mathematically that it does exist, and that's flow work. And flow work per unit mass, inside this parenthesis, everything is joules per kilogram, right? We show it by P times pressure times the specific volume, like this. PV that, let me show it this way, in, like this, the whole thing. And for energy out, it's exactly the same thing. It's Q dot out Q dot out plus W dot out plus M dot out. I'm going to do it this way. U out plus V squared over 2 out plus G Z out plus PV, the whole thing out. This is more efficient than what I did for E.N, right? Okay, that's it. Once you have all of this, you can put it together and write the first law of thermodynamics. There's one thing that you learn in thermodynamics, and that's this. That when you combine U plus PV, we also call that thing enthalpy. So I can rewrite this whole thing like these two together and these two together as H in and H out, right? So and that's what I'm going to do to write the first law of thermodynamics. So make sure you actually take notes and you write these things, and you get the mass of it, to get the algebra, how it works. And eventually you have to memorize the first law of thermodynamics. You have to commit it to the memory when you want to solve problems. That's the easy way out, to be honest with you. Okay, so let's just write the first law of thermodynamics. I'm going to use a different color because now we have the actual first law of thermodynamics. So we want to, kind of emphasize on it. The first law of thermodynamics is going to look like this. When you put the whole thing together, first law comes from this. Reynolds transport theorem says if B equals energy, then B dot in minus B dot out plus B dot gen equals dB control volume dt. As a result of that, first law becomes something like this. Q dot in minus W dot in, Q dot in minus Q dot out plus W dot in minus W dot out plus, I'm going to show the plus here because M dot in times H plus V squared over 2 plus GZ in. Now minus, that goes out of the system, M dot out, H plus V squared over 2 plus GZ out. This whole thing equals D of energy control volume dt. And what is E? E is the internal energy plus the kinetic energy plus the potential energy of the control volume, right? So in other words, if you want to show it by, it would be something like this. It would be the mass of the control volume, times internal energy plus V of the control volume squared over 2 plus GZ of the whole thing control volume, like this. That would be the first law of thermodynamics. Now this is pretty, it's pretty crowded. I'm gonna make it, simpler than what it is. And so we can actually memorize it and use it in equations. So I'm going to rewrite the first law of thermodynamics like this because it's easier, because we can memorize it this way. I'm going to rewrite it like this. I'm going to say the first law is this. Something I call Q dot net minus W dot net plus M dot in H plus V squared over 2 plus GZ minus, let me show it here. I don't have enough space, so I'm going to show it. Minus M dot out H plus V squared over 2 plus GC equals dE control volume dt. In this case, Q dot net is Q dot in minus Q dot out. Why? Because if you remember in thermodynamics, when you calculate heat transfer, if the net amount of heat transfer entered the system, we call it positive Q. Like you're like, hey, Q is plus 2 kilojoules. As you know, the system gained some heat. The opposite is like W dot net. W dot net is the opposite. W dot out minus W dot in is W dot net. Why? Because it goes back to the definition of work in thermodynamics. We say the integral of PdV. When the system is actually giving us work, we call it positive work. So W dot out is work. When a turbine generates work, that's W dot out, and it's positive based on this definition. And if you put it in this form of the first law of thermodynamics, which you can memorize easily, then it makes more sense. There's one catch to this, and I don't know if we're going to deal with that in this course or not, but there's one case that W dot out is like waste and it still is W dot out, and that's like friction. Like in pipes, when you have like head loss is W dot out. It's leaving the system, basically energy that's leaving the system. And thermodynamically, it's positive work. It's positive work that we don't get to use it, right? But it is power that is leaving the system, right? Nobody's adding like that into the system. So one thing I want to tell you, and it's very, very, very super important, is this, that you have to, this is the first law of thermodynamics, I'm going to write it here, commit this to memory. You should be able to write this equation without looking at the book. And why is it important? Because I'm going to simplify this. And after I simplify this, then we get the open system and the closed system out of it. Very, very easily. So let's do that real quick, and then we're going to be done with this section, and then we're going to move on next session doing something else. So if there are different cases that we deal with when it comes to this equation, there is this form of the equation that is first case. We call it the steady state case. The steady state case is, what's the definition of a steady state? I'm just going to give it to you, or you learn it in thermodynamics. Steady state is with this. When you look at just the control volume, if you take a picture of the control volume right now, and you look at all the properties, like temperature, like energy, like velocity, like internal energy, like density, whatever, and then you take a picture 2 minutes later, and you look at those things, you see the exact same picture in terms of all the properties. And you take a picture 10 minutes later, and you see the exact same thing. That's when you can say the process is steady state. But let me tell you this, and this is again a common problem among students. A turbine in a power plant, when we analyze it, is considered a steady state process. But people say, hey, you said steady state. Steady state means the state doesn't change. Hey, I'm sending high pressure steam into the turbine, and it comes out as like low pressure steam and low temperature steam from the turbine. The state of the steam changed. What are you talking about? You're like steady state. I say, yes, you're right. It depends how you look at the system. If you look at that mass of steam, if you follow that mass that was high pressure and went into the turbine and came out of the other side with low pressure, that system, which was 1 kilogram of the steam that I followed, that was my system. That is not a steady state case. Not at all. You have to apply the unsteady form of first law to that one. But if you just look at the turbine and you see these, the chunks of steam are coming in and are going out, they go through some changes. And yes, when you take a picture of the turbine, the first stages of the turbine, you see high pressure, and the last stages of the turbine, you see low pressure steam. That is correct. But this picture is always the same. You take a picture now, you take a picture 2 minutes later, the picture of the turbine in terms of properties and the distribution of these properties is always the same. So the average, the time average values of the properties of the control volume do not change. If you take the integral over the space everywhere of these properties, that over time, yes, the properties are changing from the first stage of the turbine to the last stage of the turbine. From place to place, the properties change. But in terms of time, the picture is the same. So always think about it this way. Take a picture now, take a picture 2 minutes later, take a look at it, I get the same picture. This is a steady state process. So when the process is steady state, then this applies to the first law of thermodynamics and every other law, and that's this, that it makes this change. dECV dt becomes 0. Simple. So the first law becomes even easier. So the right-hand side becomes easier. Now, what about a closed system? For a closed system, there is no m dot in and there is no m dot out. They are 0. You know how easy it becomes? It becomes this: q dot net minus w dot net equals dE. In this case, it becomes a system. dt. Done. This is for a closed system. And finally, this form of it, which is a closed system unsteady. The closed system unsteady happens when you closed system, but unsteady. Closed system, which this is always correct. Always correct, right? Steady or unsteady. If it's steady, the right-hand side becomes it. For a closed system that is unsteady, I can do one thing. I can take the integral. How do I do it? I'm going to show you. You see this equation? We say it's always correct, right? Okay. So I'm going to do this. I'm going to say q dot net minus w dot net, excuse me, equals dE system dt. I'm going to take the integral of this with respect to time from the initial state to the final state. Let's see how that works. From initial to final, the integral of dt from initial to final dt, and of course from initial to final dt. What do you think the integral looks like after this? It's going to look like this. If I take the integral of q dot dt, this equation here, this one that we had, what was the unit of this? This always correct equation is watts. Same case with the first law of thermodynamics. First law of thermodynamics is written in terms of watts, the one that I just showed you. But when I take the integral with respect to time, then it becomes joules. It becomes like this. Q dot becomes Q net. W dot becomes just W net. And of course, this becomes E final minus E initial, joules. That's it, done. Now there's one thing that you need to know. So the right-hand side is basically this, mass of the system times E final minus E initial, like this. In a lot of cases, if there is no change, like in the kinetic energy and potential energy, if there is no change in them, it's not like there is no potential energy or there is no kinetic energy. Yeah, there is potential and kinetic energy. They just don't change. You know? So it's like I have the system. This is a system. Like, look at this. This is a system. There's water in it. But going from, I'm heating it up, right? I'm heating it up using some flame or whatever. Let's say this is the flame. And then from state 1 to state 2, the temperature, the internal energy changes. But from state 1 to state 2, I'm not going to move this like around and, you know, change its elevation to change the, if I change the elevation of it, then the change in potential energy would be the thing. Or if I just, state 1, it was just not moving, but state 2, I'm moving it with constant speed, then that would change the kinetic energy. So there is kinetic energy and potential energy, but they don't change. Then in that case, this whole thing basically becomes mass of the system times U, internal energy of the system. U final minus U initial. It simplifies to a simpler equation. Now, just to recap the whole thing, I'm going to move to the next page to recap the whole thing. First, general form of the first law that you have to commit to memory, because you can apply it everywhere. You can go back to thermodynamics and solve all problems using this. First law, general. First law, general, watts. The unit of this equation is watts. Q dot net minus W dot net plus M dot in H plus V squared over 2 plus GZ in minus M dot out H plus V squared over 2 plus GZ out equals dE control volume dt. The unit of this is watts. Like this. First law of thermodynamics, general form, you have to memorize this. Done. That's it. Okay. Now, commit this to memory. Right. Commit it to memory. Done. Now, case 1, if you're dealing with steady state, the equation stays the same, right? But dECV over dt, right-hand side of the equation becomes 0. Good. Next case, closed system. Closed system says Q dot net minus W dot net equals dE system dt. And again, this is watts. Closed unsteady. And you might say, okay, what about closed system? Is it steady or unsteady? It's everything. It could be steady, it could be unsteady. Whatever works for you. If it's steady state, just the system becomes 0, right? So that's the general form of it. So now you know. specific case of it is Q net minus W net equals E final minus E initial. Sometimes it can be approximated by mass of the system, internal energy final, internal energy initial. One more time. Q net or Q dot net, doesn't matter, is Q in minus Q out. And W net is the opposite, W out minus W in. That's it. That's pretty much it. So I hope you took notes. And now this is the foundation. We're going to apply the first law. You have to commit that part to memory, to other equations. And we can start talking about different mechanisms of heat transfer. But this was a foundation. We had to cover it. We had to kind of do a recap of this so you guys are ready to go. All right. Okay, so this was the first session, which we went over the phenomena of heat transfer, right? And how that works. We talked about the fact that heat transfer goes from hot to cold. We talked about the applications of it. We said, why do we deal with this coarse heat transfer? Why not just thermodynamics? Because thermodynamics normally sometimes cannot calculate that heat transfer term, Q or Q dot. Or sometimes it does, but it doesn't give us like the time of it or anything. We actually want a different tool because it's important to us to know how long it takes. The rate of heat transfer matters to us. And then we went over things such as a system, an open system, a closed system, a property, intensive, extensive property, right? And eventually, like a state, a process, and the first law of thermodynamics, the general form of it, the steady state form of it, the open system form of it, and the closed system form of it, and eventually the closed system unsteady form. We did all of that. And now this is a foundation. We introduced the book. Once you get this, I hope you took notes and then you commit that equation, the first law of thermodynamics, to memory. And then we can get started on different mechanisms of heat transfer, which are conduction, radiation, and convection in general. And then there are a lot of equations and a lot of cool concepts that we're going to talk about. Well, thank you very much, and see you next session.